Yeah, hi everyone. Good afternoon. I hope you're having a great time with the talk so far. Today I'm going to be talking about PGO, that stands for Profile Guided Optimizations, and how we can leverage PGO to be able to, make Go applications which have like good performance, better performance. So a quick check: how many of you have actually used PGOs so far in any of your applications? Nice. That's a good number of people who have used it. So before we get to the talk, maybe a quick introduction about myself. My name is Nitin, and I'm a software engineer at Microsoft. I'm enthusiastic about teaching and mentoring tech students. I have mentored hundreds of students in the past. I also like to solve complex real-world problems. And a fun fact about me is I like to compile memories into photographs. I like to build stuff, and you'll always see me running on caffeine. So I was just grabbing a cup of coffee just before the talk, so that's on that. Now let's talk about the agenda and what you can expect from this talk. First of all, we're going to be talking about compiler and like what compiler is and what are the bunch of optimizations which compiler performs. And then we're going to be getting into the inline versus inlining debate, which we're going to be focusing about the hot and the cold functions. And then we'll dive deep into like profiling, like what are different kinds of profiling that you have and how you can gather all of those. And then we'll talk about how to visualize those profiles and then jump to PGO, where I'm going to be showing you a sample project that I have and how I have leveraged PGO there and to be able to get a better performance. Now, if I want to compare performance, I'm going to be diving deep into like what the numbers look like, runtime before and after optimization. And then I'm going to be sharing few insights and the lessons that I have learned in the past around PGO and optimizations. All right. Compiler. Anybody who's in tech would hear the term compiler every other day. Now, what exactly is a compiler? It's a tool or a program that converts your ideas into something that's understood by the machine. Now, let's say I want to be able to add to numbers, or I want to be able to print something as simple as hello world. Now, compiler or my computer doesn't understand that thing. Now, how do I make my computer understand that thing? So that will be through compiler. And here's a sample code of how you could be going about adding two numbers and what the corresponding assembly for the same code is going to look like. Now let's get into compiler optimizations. The code that I write or the code that you might write doesn't necessarily have to be the most optimized version of the code. So when the compiler is actually doing its thing, which is like compiling, it performs a bunch of optimizations on its own, which is something that we're going to be talking about, which will remove a bunch of efficiencies that are there in your code and make it more performant. All right. The first compiler optimization that we're going to be talking about is constant folding and propagation. I know what 5 into 2 looks like. You guys might know what 5 into 2 looks like. And the computer might also know what 5 into 2 looks like. However, when this is present in your code, the compiler will perform an optimization here, where the values will be evaluated on the compile time itself and not at the runtime. So here you can see Z will be evaluated to 5 cross 10, and it will be used throughout the code. Like wherever you have this operation, it's going to be used that way. So this is about how the compiler does the folding and then propagates that value throughout the code. Then we have dead code elimination. It's very straightforward as from the name itself. Any code that is not reachable in your application, any code which doesn't necessarily make sense, it's going to be removed when the compilation happens. For an example, if you have an if statement which will always evaluate to false, there's no point compiler would be adding that thing in the binary. So that's removed, and that's your dead code elimination. Another optimization which compiler performs is called escape analysis, where compiler makes an informed decision whether to allocate a particular function or a memory or variables. Should it be allocated on the stack or should it be allocated on the heap? Allocating on each of those has its own set of advantages and disadvantages. For an example, if I try to relate where the allocation happens, if I look at the picture on the left, the compiler is going to be putting the data and then the value on the stack itself, because once I return from the stack, I no longer need that value. However, that's a different case when we have in the other side. So here, the compiler is going to be putting the value D on the heap. The reason being, create data function is returning reference to the memory. So I cannot afford, meaning compiler cannot afford to lose the reference to that variable. So that's the reason it's placed on the heap and it stays there until garbage collection takes action. Another optimization that we have is called register allocation, where compiler would want to perform few operations. For example, if you want to perform a mathematical operation, it would do that in the registers itself instead of doing it in, let's say, the memories which are farther away from your code, which could be like a memory, stack, or heap. Then let's get into inlining, a very famous compiler optimization that happens. It's as simple as bringing the definition of a particular function to the place where it's being invoked actually. So here I have two functions, Celsius to Fahrenheit and Fahrenheit to Celsius. These are the functions that I've defined. Now what compiler will do during compiler optimization here is that the definition of these functions would actually be brought into the code as if those definitions actually existed there. So once inlining takes action, this is what your code is going to be looking like. We'll have the two implementations brought where these functions are actually getting involved. It is as simple as that, but for compiler, it's not necessarily as simple. Now, the question here is, it's more like a debate, which functions do you actually inline? Your code might be having like thousands and 2000s of functions. Should all the functions be inlined, or should it be like specific functions be inlined? And how do you figure that information out, like which function do you want to inline? For an example, you have a function that's being called at 10 different places in your code. If you were to inline that function everywhere, that would mean the definition of that function would be brought to wherever it's being invoked. Now that would also mean there are more lines of code in your application. Now that would also mean that will lead to a bloated memory. Now, and on smaller devices, it could even lead to thrashing, page faults, and cache faults, right? So that is something where compiler makes a very informed decision here, not to inline all functions, but only the functions which are hot. Hot as in the functions that are invoked too many times, the functions which are regularly invoked, the functions which have, are called a lot of times. So that's where we differentiate, meaning the compiler differentiates what a hot function is and what a cold function is, and how do we go about inlining those functions. Now, throughout the discussion that we've had so far in terms of the different kinds of compiler optimizations, one thing was very evident, which was that functions are very integral to how compiler optimization works. The way you can think of it is, all the optimizations that we've talked about so far applies within the scope of a function. And that's a reason where it would make sense to optimize a function to be able to get a highly performant co-applications. Now we've talked about compiler, we've talked about what are the different optimizations that compiler performs, like how inlining happens, which functions are inlined, which functions are not inlined. And before we get into PGO, which has a term profile, we're going to be talking about like what the power of profiling is and what the different kinds of profiling that you have. Profiling is nothing where you would want to identify the performance bottlenecks in your Go application to be able to build faster performant applications. And Go has a pprof profiler which you could be using to gather profiles. Now the question here is which profile, because there could be like so many profiles that could be there. So you could be getting your CPU runtime footages, you could be getting your memory footprints, you could be getting your block footprints, and as well as profiling around Go routines. So these are the different options that we have when we talk about profiling. Now somebody who is new to profiling, how do they go about starting their profiling journey? They have their Go application. Let's say I have a Go application and I want to know how do I gather those profiles. So we have at a very high level 3 options which you could be using to be able to get the profiles. The first being you could be writing your tests, you could be writing your benchmarks and then get the CPU profile or even your memory profile. And the way you do it is you pass certain flags there. For example, you could be passing CPU profile flag to get your CPU footprint, or you could be passing memory profile flag to be able to get your memory footprint. Another way that you have to get your profile is by blank importing net HTTP pprof endpoint. And the way it works is it would inject an endpoint to your Go application, and you could be hitting those endpoints to be able to get the necessary profile that you could be looking for. It could be your profiling around Go routines, it could be your profiling around heap, around stack, around garbage collection, and all of that. And then, of course, there's also a runtime package that we have in Go, which you could be using to start your profile, end your profile, and then collecting those traces. And these profiles are then further analyzed by using Go tool pprof. Now, there is no one specific way or one specific option that you could be using to collect your profiles. somebody might want to go for the first option where they would want to create benchmarks. Somebody else might be wanting to go for another option where they're importing blank HTTP, the endpoint. So how do we go about choosing what's right and what's wrong? I mean, there's nothing wrong about choosing one option over the another. It highly depends on the nature of your Go application. Each of these have its advantages and disadvantages. For example, if I talk about the second option where you're importing HTTP prof package, in your Go application, you might want to make sure that not everybody has access to the profiling data. And the way you do it, you would have to create some middlewares to be able to have the right set of authentication and authorization there. If you talk about the benchmarks, their disadvantages is that you could only be profiling a particular block of code or a particular function and not necessarily get an entire picture of the whole Go application. So that is the reason selecting the good profiling tool is really important, and it's highly dependent on your application. Now, how do you go about visualizing these profiles? I have my profiles. I know what profiles are. I know what are the different kinds of profiles I could be collecting. And now I have actually collected the profile. So how do I visualize that? I need to extract information out of it. So one of the way that you have is you could be building flame graphs out of it. So this is what flame graph looks like. So on the x-axis, you have the duration of time. This is generally confused with like the passage of time, but that's not the case. It's the duration of time. I'm saying, okay, for the last 30 seconds where I have collected my profile, these are what the runtime stack traces look like. And again, your x-axis represents the stack. The color here doesn't necessarily have to mean anything. The idea was we wanted to represent, the flame graphs had to represent like what's hot on the stack, and there's no better color to represent hot than your yellow or red or orange for that matter. Then we have another way where you could be using SVGs to get information about your profiles, where each block represents a particular block of code and it splits into multiple, like think of it like a tree, and then you could be looking at each node and see how much time does that node actually take and how much time does the individual node spinning out of it take. So that's about your SVGs. So we've talked about profile, we've talked about optimization. Now let's get to the point where we are actually be unlocking the power of profile guided optimization. So this is how Go official documentation describes profile guided optimization. Me and we could be having a Go application running in production. Now what we are going to do is we're going to be getting profiles information from it. Now, how would you be getting those profiles? So we would go back to the slides, 2 slides back, where we have like bunch of options where you could be collecting the profiles. Okay, all right. Now we are done with step number 2. Now let's say you would want to release or make a new release of your Go application. When you're actually compiling and building the binary, so you could be feeding this profile that you have collected to be able to make it more performant. So we'll talk about how it's more performant and what all things happen behind the scenes so that it's more performant. But this is what the entire flow looks like. And there's like a loop over here. So you collect profiles, you build again. You collect profiles, you build again. And if we look carefully, this looks something like a loop. So from step number 2, we go to step number 3, and then again to 2, 3, 2, 3. So it's a whole loop. And that is the reason PGO is also known as feedback directed loop. So these are the terms that are used interchangeably. Now let us take an example of a sample Go project. So I have called it MAM Vault API, which offers a bunch of API suites for you to be able to perform some API operations. So I have the root endpoint, which performs some operating system level operations like listing files in a particular directory, and then the get endpoint will let you get a value for a key. There's a set endpoint that you could be using to set a value for a key, and then you could be using get all API to be able to get all the key and values that you have created so far. And this basically uses in-memory cache along with data store for you to be able to manage your key and applications. Okay, let's see what happened over here. I build my application. I'm saying, okay, GC flex -m, which would mean I would want to get information about how the compiler is doing these building behind the scenes. And towards the top, you see a bunch of inlining that happened. There are a few functions which got inline, datastore.new cache and other functions. And then there's also information regarding how some of the variables or some of the literals are escaping to heap. Now, if you remember, like a couple slides back, we talked about escape analysis, where compiler makes an informed decision whether or not to allocate a particular function or a literal or a variable on stack or heap. So this is where you could be seeing those information, like where exactly that particular variable got escaped. If I look at this line, like third line from the bottom or the fourth line, server is starting on port 8087. So here we are saying this got escaped to heap, meaning I would want that information even after the scope of the function got over. So that's the reason it did not go to the stack itself. All right. Now let's see what happened over here. I built my Go binary, I started it, I got an information saying server has started on port 8087, and this is what the landing page of my Go application looks like. I am not sure if you're going to be able to see the entire thing, but like I mentioned earlier, it's going to perform some bunch of operating system level calls. You could be getting your files in the directory, print some environment variables and stuff like that. Now let's get to the process where I would want to collect my profiles. Now, I want to simulate an environment where my application would behave like it's in production. So for that, what I've done is I have put some load onto my Go application. Like I told earlier, my application is running on localhost 8087. So what I'm essentially doing here is, for 30 seconds, I'm putting load on my application, which is spinning a bunch of tests and Go routines to be able to get that load. Now I have my Go application, it's running, the load is there, the payload is there. What happens next? Now I would want to collect profile. Now how do I collect my profile? I'm just using a curl operation here and saying, okay, go ahead, collect my profile and put it in a file called no_pgo. I'm going to be using two types of terms here, no PGO and with PGO, to be able to differentiate this was before applying PGO or was it after applying PGO. And if we see at the endpoint that I'm trying to hit, it's debug/pprof/profile, which basically is your option number 2 that I talked about in the profiling journey, like how I could be importing my blank HTTP pprof endpoint, and it would expose few endpoints, and I could be hitting those, and then trying to get my profiles. And here I'm doing it for the last 5 seconds. I'm trying to extract profile out of it. So which has in turn created a no_pgo.pprof file, and let's say I rename it to or move it to a file called default.pgo. We're going to be understanding the significance of this file once we actually get to pgo. So far what you've seen is application was there, it's running, I have put some load on it, I've collected some profile, and towards the end, I have a file called default.pgo. Now let's talk about how I would want to power this application with profile guided optimization. And let's actually get to the point where we would be using pgo to fasten up our application. Let's see what's happening over here. Again, I'm doing the similar thing. I'm trying to build my Go application, but this time if you see, there is some additional flag that have passed over here. -pgo is equals to auto. And if you think about the 2 slides back, there was a file called default.pgo. So that is where it's actually being used, meaning I'm saying to my compiler, hey, this time when you compile or make a binary for my Go application, just make sure to include the -pgo flag, which would mean the default.pgo file, the profile that I collected, should be used over here. And again, you see the similar thing here. There's like bunch of inlining messages that you have. There's bunch of information about how some of those variables are escaping to heap or stack for that matter. Now, I want to make sure the default.pgo file that I used, it's actually being considered by the compiler when it's, creating a binary. So for that reason, I'm trying to build up, trying to extract a bunch of flags that were used. And if I look at the flag pgo, it says, okay, my default.pgo file that I created, collected the profiles and moved it to default.pgo was actually used for my Go application. Okay, well and good. It used that application. How did the performance become faster? Did it become faster? Yes or no? Now let's get to the answer to that question. But before that, we're going to be diving deep into what happened exactly over here. So towards the left, I have the bunch of inlined functions that happened before applying pgo. And then towards the right, I have a bunch of like functions which got inlined. And there's a difference between how inlining happened before applying pgo. Pgo is a profile guided optimization. I'm going to be using the short term. And then towards the right, you have the functions which got inlined after. And there is a difference here. As I've highlighted in the red color, there was a function handler.handleGetAll, which was basically a function that I was using to get all the key value pairs that I have in my cache as well as data store. So that is what also got inlined here. So now, what compiler did was like, okay, this function is getting invoked too many times, meaning this function is hot in nature. So why don't I go ahead and just inline that function? So that was the decision which compiler took after we applied Pigo, and that's the whole story behind Pigo. So now I have two files over here. One was the binary which I had before applying Pigo, and one is the binary that I had after applying Pigo. One thing to note here is that there is also a decrease or an increase in the size of these binaries. So we can see that some of the binary that we have built has increased in size by almost like 100 KB. Anybody would want to guess like why did the size of the binary increase after applying Pigo? Sorry? Exactly. So the functions got inlined, meaning the definition of those functions now came into the code itself, which ultimately means the size of my code increased, and of course, the binary size increased as well. So that's the explanation for that. Now let's see what's happening over here. I ran my Go application. It says, okay, well, your application is running on port 8087. I'm doing the similar thing over here. For the 30 seconds, I'm trying to put a load on my application. It performs some bunch of like Go routines behind the scenes, and then I'm doing nothing major, nothing significant here. I'm repeating the same thing. Now, the thing is, when my application is running, the binary was built with Pigo. So I'm collecting those profiles for the last 5 seconds, hitting the debug pprof profile endpoint, and getting my profiles. And those profiles will be stored in withpigo.pprof file. So we've reached a stage in the project where I have my profiles before applying Pigo, and I also have my profiles after applying Pigo. Now I would want to compare those profiles. So what I'm going to be doing is I'll use go-tool pprof command, and then getting the profile information for both the profiles that I've collected so far. If we look carefully, towards the left we have like what happened before Pigo, and towards the right we have what happened after Pigo. I'm trying to get runtime information for the top 10 functions, which is, as you can see over here. So there was a function called runtime.cgo call, which was taking 4,140 seconds before I applied Pigo. And now it's taking 4,081 seconds. So that's a decrease in around 58 seconds in terms of how much this function actually took time. And similarly, you could be looking at other functions and then trying to get that information. Okay, this function was taking that much amount of time before applying Pigo. Well, now this function is taking less time. So there is something that has happened. And the magic that has happened here is your profile guided optimizations. Because this time, when I build my binary, I told my compiler, okay, you're going to be using the default.pigo file, you're going to be getting information out of it, and make sure you make sense out of it, perform the optimizations that you do best, and get the binary. However, if we also look at some of the functions over here, for example, if I look at the runtime.standardCall0 function, the time actually increased. Like PGO was supposed to decrease the time, but now it's unfortunately increased. So anybody would want to make a guess, like why is it like, is PGO not working, or did I do something wrong? Like what happened here? Like why did the time actually increase?
You have more free CPU time.
Sorry?
You have now more CPU time. So you save the CPU in other functions.
Exactly. So now, like he mentioned, we're going to be having more CPU time. And one thing to note here is that compiler performs these optimizations based on its heuristics. And this time, it just happened to perform this way. So that's how we're going to be saying, this function took more time this time. Now let's compare the execution time of two functions. So as I talked about earlier, there's going to be a getAll endpoint in my Go application, which is going to be giving me all the key and the value pairs that I have. It will first try to get it from the cache, and if not, it's going to be getting it from the data store. And if I look at the time over here, there's a function called get all key values. The time decreased from 110 millisecond to 100 millisecond. This function isn't doing anything great over here. It's performed just bunch of smaller things over here. So even this function has a decrease in 10 millisecond of time. Now think of it when it's actually applied to like on a bigger screen, your Go application having thousands of functionalities, having hundreds of functions, and is being used by millions of users. So this is bound to make sense once you actually get to that level of your PGO optimizations. Okay, now let's try to quantify the numbers, right? What does it mean? Okay, I'm saying the function execution time decreased by 60 seconds. What does it mean? So this is how some of the time of the functions have decreased. We have something like minus 58 seconds. We have something like minus 11 seconds. All those functions decreased in the time. But there is one function that we already talked about earlier, which actually increased in time. And if we try to compare or perform, the percentage out of it, so we are able to see performance improvement as big as 8 to 11%. This is when it's applied to an application running in a very simulated environment. I'm just trying to put a bunch of load to the application and then getting the profile out of it. If it were to be applied on an application serving millions of users, or it has like thousands of functionalities, hundreds of functions, even an increment of 1% or 2% is going to be a miracle. So that's about the performances. Now I would want to talk about some of the optimization insights and the lessons that I have learned so far in my Go journey, where you could be getting better performance. The first one is use benchmarks and create CPU profile and memory profile. I cannot emphasize enough on how important it is for you to be able to create the benchmarks. Let's say you realize, okay, this particular function is slow, or this is taking a lot of memory footprints, or this isn't behaving as good as it was supposed to behave. How do you go about getting that information out of it? So one thing that you could be doing is you could be benchmarking, where you try to simulate an environment. You could be simulating an environment where you try to compare the actual performance of this function to what it would behave like. Then you could also be monitoring the memory allocations. This is absolute favorite thing of mine, because sometimes I don't necessarily focus on the CPU time, but I also make sure the locations or the memory allocations that are happening in my applications are as less as possible. So this is where I always try to take a look at, okay, what are my memory allocations looking like? Is there a way I could be reducing that? Where is a bunch of my memory getting allocated? So all those things can be answered with this thing. Next thing is make careful optimizations. It is one thing to optimize your code, but it is another thing to make premature optimizations. You do not want to improve the performance of one function, optimize one function or part of code, but at the same time you are affecting other part of your code. So it's really important that you think and act in that sense, and then try to be able to make those optimizations. Next thing is disassembly. How many of you have actually used disassembly? Great. I would recommend every one of you to start using it, because of how much helpful it can be for you. Because I understand the output of disassembly of a particular function isn't necessarily user friendly. You might get overwhelmed with all those things that are happening, but at the end of the day, you might want to identify one bottleneck. So you would want to get more information there. And then, of course, you have something called caching. This is my go-to. If somebody is saying, okay, this function is not performing better, or this application is not performing better, I'll be like, I'll use caching. As simple as that. My absolute favorite thing to do in an application, and to be able to optimize its performance. So yeah, so these were the bunch of lessons that I wanted to share, and share and then get insights into all of these. So with that, we have come to the end of the presentation. I hope you all like it, and I hope you have amazing time with the rest of the talks. Thank you.